The goal of this part of the class is to derive the Fokker-Planck equation from Ito calculus. So remember that we have seen before how to write Ito formula for any function f. Any function f, the Ito calculus says so. Let's start with the following stochastic process. X dot equals b of x plus we'll say sigma w dot, where b is a drift and sigma is a diffusion tensor. So in that case, the Ito formula can be written as, so we're in n dimension, so this is, we're in the open set, let's call it omega, and in that case df can be written as L star of f dt plus the noise term, which is ddf dxi multiplied by sigma dw I. We have to sum from 1 to n. So this is true for any regular function f, which is, let's say, at least, we don't care really, at least C3 in omega. So now we are going to use it and write what is f of x of t minus f of x of 0. And for this, we'll write it, we'll use the Ito formula. This is the integration from 0 to t of df of at the point x of s ds. So now we are going to take the expectation of this and look at each term separately. So let's take the expectation with respect here with all trajectories that start, let's say, from point x. So this is expectation of x, f of x of t. So condition that, let's say, x 0, the particle, is located at point x. So minus, of course, this is nothing but minus f of x, because x0 is exactly equal to this, plus, so equals the integration from 0 to t of the expectation of d of x of s ds of x of s ds. Right, so now the idea is to treat specifically this term and to look exactly at what we get. So let's do that in the next slide. So we now have to integrate, so let's write it this way: expectation of f of x of t minus f of x equals, so we have to integrate from 0 to t. And now let's write what is the operator L star that we have seen before. This is ddf dxi dxj, and then we have sigma transpose sigma ij divided by 2, and then we have to sum over I and j, so we have the expectation here at the position x of s plus b I x of s ddf dxi x of s ds, plus we have to keep the expectation of integration from 0 to t of the noise of the stochastic term, which, as we have seen before, d of x of s, let's write it sigma d omega I. So again, as we have seen, when we take the expectation of this, it can go inside. And because this is in the class of the non-anticipating function, and because the expectation of this and this are independent, and of course using that the expectation of d omega I, this is 0, then this term is going to be 0. Now, what is the meaning of the expectation of the first term here? So to understand this, what we need is basically to remember that we have introduced the probability density function p of x of t to be located at x plus dx, x plus dx, condition that the process started at position x, that this is actually can be written as the probability density function to jump from, let's say, suppose you start at y, so that will make it so starting from y, you jump to x in time t. This is dx. So actually, the expectation of x, f, x, and t let me erase this part here, this is not. So again, of f, x, and t, this is precisely the integral of p, so condition of starting at position y. This is precisely f of x, probability of making a transition from x to y, from y to x, dx. Right? And this is integration over the domain. So now we are going to discuss this term here. So to do this and to derive the general equation, what we need is to calculate the expectation of the integration from 0 to t of sigma transpose ddf dxi of x of s. This is ds, so divided by 2, plus, so we have to sum this ij di dij, and plus the sum of bi ddf dxi, and this is ds. So obviously this can be written as the integration from 0 to t of the expectation of what we have in here. So this is not going to repeat all of these, ds, plus the same here. Now, if we use it by the definition of expectation, this can be written as the integration from 0 to t of sigma transpose divided by 2 ddf dxi dxj at point x and x multiplied by the probability density function to jump from y, to have a transition from y to x. Wait, this is at s ds plus, so, and this has to be the sum from I and j plus the sum for I of bi of x df dxi p t x and y, and then we have to multiply here by ds, and this is s. All right, so at this point we are going to have this, which has to be equal to what we have shown before. This is the integration over omega of the function f of x, p, t, x, and y, and this is dx, and this was minus f of x, and this has to be true, and everything has to be true for any function f, the regular function, and we can take them as with compact support on omega. So now to have such identity, this equal to here, to obtain the equation, we're going to integrate by parts this term twice, and this, so twice, and this only once. So now I'm going to neglect all boundary terms, because we can take f with compact support. So by integrating this term twice, okay, and I forgot here to use, this is also integration over omega, and this is also integration over omega. So this is going to be integration from 0 to t of sigma transpose sigma at position x divided by 2 multiplied by p s x of y, and now we have to derive outside dxi dxj, and this is the sum over I and j, and now we can multiply everything by the function f of x, and here by just deriving, and so we have also an integration here over omega plus again the integration over omega, so this is dx, integration over omega of bi of x ps of x and I, and now this is ddxi, the sum over I, and now this multiplied by f d of x. So for this term, for this to be equal to that term that, let me highlight it here in red, to be equal to all of this, we need to have what we have here inside, the term that are here, to be equal to what we have here inside, right? And this is what we are going to do next. So let's go back and discuss the boundary condition later. So now we are going to have the expectation. Let's go directly to let's take first the derivative with respect to time. So the derivative with respect to time will give us dp dt. I can derive, I have changed the integration, and with I commute with the derivative. So we are going to get integration of dp dt for all function f of x, and this is x and y and t, dx equals, so now I can remove, so you remember the previous term, there was an integration from 0 to t. So this will now be removed, and we'll have something equals the term here that we have calculated, and this will be true for all function f of x dx. So finally, this will give that dp dt equals L of p, where the operator L is exactly the sum of ddu dxi dxj multiplied by sigma transpose sigma divided by 2 multiplied by p minus b of I p, and this is the sum d dxi, and here we have to sum over ij from 1 to the dimension of omega. So this is precisely the Fokker-Planck equation. It says that the probability to have a transition from point y to be located in this small element of volume x plus dx, to have such a transition occurring at time t, so this is pt of x of y, satisfy this following partial differential equation. So this is true for all point x in here. So remember, this is p. So this is true for p, which is here a function of x and y, and as time t goes to 0, you can show as an exercise that p x and y as t goes to 0 converges to delta Dirac of x of y as t goes to 0. Now the question is, so what are the boundary conditions for this equation? So again, we have the Fokker-Planck equation, which is dp dt equals, let me write it, L of p, such that p, we can go to the limit p0 of x and y. This is delta of x minus y. And now the question is, what are the boundary conditions to put here on the boundary, d omega? So in general, if the particle is reflected, for a reflected particle, the probability flux should be 0. That is, this can also be written minus divergence of j, where j is the flux, the probability flux. So the condition is that j dot normal, this vector j dot n, equals 0, which can be written as d dxi sigma sigma transpose divided by 2p applied to ni, so we have to sum over I, minus b, the field, dot n, multiplied by p, has to be equal, so this is for t and t, x and y, has to be equal to 0. So we started this, say you start at point y, and this is true for all point x on the boundary. Right, so this is an example of reflecting boundary condition. If on the other hand we impose an absorbing boundary condition, so what's the absorbing boundary condition says? So the absorbing boundary condition tells us that p, t at x and y has to be equal to 0. That is, when you start at any point y on the boundary, the probability to make a transition to any point inside has to be 0. So this is called the absorbing boundary condition. Alright, so we have seen today the derivation of this Fokker-Planck equation, and we discuss here two types of boundary condition, either reflecting one or the absorbing one. So there are two. Alright, so I'll see you for the next class.